Good day, students. Welcome to part 6 of the AP Calc AV multiple choice practice for 1969. We're going to be going over questions 26 to 30 in this installment. All right, so let's go ahead and take a look at question 26. We're supposed to find the definite integral from 0 to 1 of the square root of x squared minus 2x plus 1. All right, so in order to do this, we need to simplify this integral. We can't use u substitution here because if I differentiate the inner function, the function that the radical function is being composed with, I'll end up with 2x minus 2, and that's not a multiple of the x. Okay, so u substitution will not work here. So how about I factor this quadratic trinomial and see maybe it can be in a form where I can reduce this whole expression, all right? So if you look at this, this is a perfect square trinomial. So um, if you remember the factorization of perfect square trinomials, if you have anything of the form a squared minus 2ab plus b squared, that simply factors directly into a minus b squared. Okay? So let's assume that you didn't know this trick. If you knew this trick, then you could just factor this into x minus 1 squared in a snap. But let's assume that we didn't know this factorization trick right here. So I'll just use my x game, x squared minus 2x plus 1. So I like to use the AC method to factor trinomials. So AC goes on top, which is 1, and B is negative 2. All right? So what's the numbers multiply to give you 1 and add to give you negative 2, negative 1 and negative 1. And we can just factor this into x minus 1 times x minus 1. And we can see that the radicand is x minus 1 squared. Okay? All right, so now we're going to rewrite this, the integral from 0 to 1 of the square root of x squared minus 2x plus 1 dx. I'm going to rewrite the original problem, replacing this piece with a factored expression, okay? So it's going to become the integral from 0 to 1 of the square root of x minus 1 squared dx, okay? So what does this become? Remember, anytime you take the square root of a square, you have an absolute value situation. So this is going to be the square root from 0 to 1. The square root and the square cancel out, and you're going to be left with the absolute value of x minus 1 dx. Okay? All right. Now, we know that the absolute value is a piecewise defined function. It's a combination of two functions with two linear functions with opposite slopes. So we're dealing with this case from 0 to 1. So we know for the absolute value function, the break happens at 1. All right, so let me draw a line to show you something real quick. So for absolute value, the v, or the corner, the vertex, happens when x minus 1 equals 0, which is 1. So to the left of this absolute value expression is going to be negative, and then to the right is going to be positive. All right, so this absolute value is basically negative x minus 1 to the left, and then to the right is x minus 1. All right. Okay, so since we're dealing with the integral from 0 to 1, we're going to be adopting the negative sign here. So this problem becomes, we can write it as the integral from 0 to 1 of plus or minus x minus 1 dx. But since we're going to the left side of where the sign change happens, we're going to have, it's going to become negative 0 to 1 of x minus 1, okay, dx. All right, so we can take out this minus, factor out this minus, and then write this as negative integral from 0 to 1 of x minus 1 dx. Okay, so again, do term by term integration here. You can do the x and then the 1 using the power rule for integration. Okay, so we're going to have negative of the antiderivative of x is simply x squared over 2, and then the antiderivative of 1 is going to simply be x. We're evaluating this from 0 to 1. Alright, so using FTC part 2, we're going to have minus, parentheses, 1 squared over 2 minus 1, plugging in the upper limit of integration, which is 1, minus if I plug in the lower limit of integration 0, I have 0 squared over 2 minus, but there was a minus in front, so this becomes a plus 0. Okay? All right, so that there we're going to have negative 1/2 minus 1. Well, this is 0, so it goes away. And we can have minus 1/2 minus 1 is negative 1/2. And then if you multiply this 2, you end up with 1/2. Okay? So there goes your answer. Your answer is option C. All right, let's go ahead and take a look at the next question, question 27. It says if dy dx equals tan x, then, now if you have your table of derivatives memorized, you automatically know that this is going to be ln x plus c, because the antiderivative of tan x is equal to, tan x dx is equal to the natural logarithm of actually negative natural logarithm of the absolute value of cosine x plus c, and this is also the same thing as the natural logarithm of the absolute value of secant x plus c. Okay? Alright. I'm going to show you in a minute how this comes to this. Alright, so if you knew your rules, integration rules, you can just directly know what the answer is just by looking at it. But let's assume that we don't know the rules, okay? Alright, so let's go ahead and solve the problem. You're told that dy dx equals tan x. So what is y? So I want to isolate y, so I need to do the opposite, the inverse operation of differentiation, which is basically integration. So I need to integrate both sides, all right? So I'm going to integrate the left side, dx, and I'm also going to integrate the right side, dx, okay, to get y isolated. All right, so the dx is canceled out here. The antiderivative of dy is just simply y. And on the left side, we have this indefinite integral of tan x dx. All right? So I'm going to use the quotient identity of quotient trig identity to express this in the form the antiderivative of tan is sine over cosine, right? Sine x over cosine x dx. All right, so can I use a use substitution here? The question is, if I differentiate one function, do I get the other function multiplied by dx? That's the question. So let's say I set u to sine x. If I differentiate this, the u is going to be cosine x dx. But in this case, we have dx over cosine x. This is not equal to dx over cosine x, right? So I can't do that. How about I pick a different u? What if I say, oh wait, let cosine x be my u? Do I get the other function times dx? So du is going to be negative sine x dx, which is perfect, right? Sine x dx, you can resolve the sign by dividing both sides by negative, and that will basically make negative du be our substitution. Okay, so we can use substitution here, because if I pick one function as u, the derivative is the other function multiplied by dx. All right? Okay, so let's go ahead and do that. I'm going to call use substitution here. U is going to be cosine x, like we just found out. And then du is going to be negative sine x dx. And I just have sine x dx. I don't have a negative here, so I have to divide by negative 1. So negative du equals sine x dx. All right, so I'm going to go ahead and make my u substitution here. So this whole integral now becomes the indefinite integral of cosine x will become u, and then this entire numerator will become du. So we have du over u. Okay? All right, or we can write this as, just to make it clear what's going on, integral of 1 over u du. Okay? So what's the integral of 1 over u? It's simply the natural logarithm of the absolute value of u plus c. Okay? Now we've got to plug in the value of u back into our answer. U is cosine x, so let's plug that in. So our answer is going to be the natural logarithm of cosine x plus c. Okay? All right. Now, if you look at all the options we have here, there isn't any cosine. What we're gonna do, I'm sorry, there is a cosine. Oh yeah, I made a mistake. What happened is as follows. Let's see. Negative du. I supposed to have a negative here in my substitution. Sorry about that. So there's a negative du, so that negative carries over here, so the negative carries over here. Okay, good. I thought I was looking at d, I was like, oh man. Anyway, so there's no minus here, so the answer is not d. This is just a distraction. Just like in case you made a mistake, I just made a forgetting that minus there. So how do I make this? How do I make this into another form? You just use the exponent, the power property of logarithms. I can write this as a natural logarithm of the absolute value of cosine x to the negative 1 power. Okay? Cosine x to the negative 1. Let me put the negative 1 outside. Doesn't really matter. But so, natural logarithm of the absolute value of cosine x to the negative 1 plus c. Okay, so there's, because imagine there's a negative 1 right here, and then you can just power it up to the as a power of cosine. So you have this. Alright, so using the quotient property of identities, the quotient property of logarithms, right? This one, the reciprocal property, reciprocal trig identity, I can write this as a natural logarithm of the absolute value of secant x plus c, right? Because we know that cosine to the negative 1 of x is the same thing as 1 over cosine x, right? And then that is the same thing as secant x. So this entire expression right here is the same thing as secant x. Alright, so if you have this memorized, you don't have to do all this work, but I'll just show you just to let you know. So this is the answer, natural logarithm of secant x plus c, or negative ln of absolute value of cosine x plus c. So our answer is option letter C. Alright, let's move on to question number 28. It says a function defined by f of x equals root 3 cosine x plus 3 sine x has an amplitude of. Now this is a kind of a weird problem, but let's go ahead and take a look at it. Now if you look at this function, it looks very much like the sum identity for sine. So remember sine x plus y is equal to what? Is sine x cosine y plus cosine x sine y. Alright? So this is a sum identity we're all used to, but if you look at the way it's set up here, I'm going to rewrite this in a method that's consistent with how it's set up here. So how about I use sine, using commutative property of addition, y plus x, okay? Sine y plus x, I'm going to, just basically switches the order of things. So it's going to be sine y cosine x plus cosine y sine x. Okay, it's the same thing as this. I just use the commutative property of multiplication and addition to switch this order. Now, why did I do that? Well, check this out. I'm going to put this function down here. And this function is root 3 cosine x plus 3 sine x. Okay, so we can see that I can match up my sine and cosine. I can have my sine y be equal to root 3 and cosine y be equal to 3. But that's a problem. That's a problem because we know that the range of sine x is between negative 1 and 1. This is way outside the range of sine x, okay? So what I have to do is I know that these two satisfy, to find the radius, right? To find the radius, we know the formula R. There's a Pythagorean relationship, x squared plus y squared. And we know that this is the y coordinate and this is the x coordinate. So if I plug in these two into this equation, I can multiply this expression by a multiple of the radius, and that will basically make it possible for me to scale this down into a version where I can have a sine assignment that's within the range of the sine function. All right. So let's go ahead and find that radius value that I'm going to use to manipulate to scale these two down. So in this case, we're going to use the Pythagorean identity to find out what that r is. So x is going to be cosine y, which is 3 squared, plus y was r squared 2, plus y, which is root 3 squared. Okay. All right. So now we have r squared equals 9 plus 3. That equals 12. So r squared is going to be 12 in a root both sides. And then you have r equals, if you simplify, 12 is 2 root 3. Okay? All right, so now I can now multiply this uh, the function I have with 2 root 3, the numerator and the denominator without changing it. So 2 root 3 over 2 root 3 times root 3 cosine x plus 3 sine x. Okay, so I'm going to remember the goal here is I want to scale it down so that I can have valid cosine assignments. All right, so let's leave the numerator out there and then I'll distribute the denominator. So we're going to have 2 root 3 times root 3 over 2 root 3. See that cosine, this first term is going to be scaled down by that, plus 3 over 2 root 3 sine x. All right, so let's simplify this a little bit to see if I can express this as a sum identities for sine, then I can then determine my amplitude. All right, so this is going to become 2 root 3. This root 3's cancel out, so you have 1/2 cosine x. This is excellent because I know that sine can assume a value of 1/2 in its domain. Sine of 30 degrees, for example, or pi over 6 is 1/2, which is nice. And then this piece right here, I can rationalize the denominator, multiply by root 3 top and bottom. So that's going to give me 3 root 3 over 6 sine x. And then simplify a little bit further, we have 2 root 3 over 1/2 cosine x plus 3 goes here, 1 and 3 goes here twice, root 3 over 2 sine x. Okay, now let's do what we did before again. Can we express this as, can I assign this as sine and cosine? Can I say this is sine y and this cosine x, sine cosine y? Can I say that? So the question is, sine y equals 1/2. Does that make sense? That makes perfect sense, right? So if this is the case, that means that y is going to basically be the inverse sine of 1/2. All right. So we have sine y with this condition times cosine x plus cosine y sine x. We already know what y is. Y is the inverse sine of 1/2, or it could be the inverse sine over 3 over 2. It's going to be the same thing, 30 degrees, times 2 root 3. Okay? So now what can I express this as? Well, hey, I can use the sum identities working backwards. This is going to be 2 root 3 times sine x, sine y plus x, sorry, sine y plus x. But think about it, what is the maximum output for a sine function? The sine function the maximum is 1 or -1, right? Since this has a maximum of sine and 1 and -1, what does that mean? It means that if you multiply the maximum by 2 root 3, it's going to be 2 root 3, and the minimum is going to be -2 root 3, all right? So what does that tell me? That tells me that the amplitude is simply 2 root 3, because sine is always in between 1 and -1, and this just makes it higher or lower, all right? So there goes your amplitude, 2 root 3. So our answer is going to be option C. All right, let's move along to question number 29. So we are asked to find the antiderivative of this function. So let's see. We can convert this into cotangent, but that requires knowing our Integration rules for cotangent, which is one way of doing it, but let's use a u substitution here. Let's see. Can I use a u substitution to evaluate this integral? Basically, if I take one function, can I pick one function, numerator or denominator, in such a way that when I differentiate it, I get the other function multiplied by the x? That's the question. So what if I pick u as the denominator? U is sine x. If I differentiate this, do I get cosine, the second function multiplied by the x? So the u, derivative of sine x is cosine x dx. That's perfectly what I want, because that's what the numerator is, right? The numerator is a nice du. Fits perfectly. So we can use u substitution in this problem. All right, so using this u substitution here, we also have to go ahead and change our limits of integration when we're using the u substitution. So let's do this. So u is sine x, then uh, we know that x is pi over 2, that's the upper limit, and then u is going to be sine of pi over 2. And then I like to use my curve to do this. Sine of pi over 2 is 1, so u is going to be 1. That's the upper limit, and then the lower limit, pi over 4. Uh, the, the lower limit of u is going to be sine of pi over 4, and we'll know that is root 2 over 2. Alright, so let's go ahead and change this into a u substitution problem. So it's going to be the integral from root 2 over 2 all the way to 1 of 1 over u du. Alright? Okay, so what's the antiderivative of 1 over u? It's going to become the natural logarithm of the absolute value of u evaluated from root 2 over 2 to 1. Okay? So what we're going to do here is we're going to, alright, so applying FTC part 2, this is going to become the natural logarithm of the absolute value of the upper limit, 1, minus the natural logarithm of the lower limit, which is root 2 over 2. Okay? Alright, now what does this become? Natural logarithm of 1 is 0, minus the natural logarithm of root 2 over 2. This is a positive number. If you take the absolute value, this is what you get. Alright? So that's basically equal to negative natural logarithm of root 2 over 2. Alright, so let's see. We don't have a match here, so we need to do some more work with this problem. So we're going to use the power property of logarithms. This minus right here, I can already say the natural logarithm of root 2 over 2 raised to the negative 1. Okay, like the other problem we did, you can imagine that there's a 1 over here, and then you just power it up using the power property or exponent property of logarithms, alright? So this negative 1 means you just reciprocate this argument in this parenthesis, so you have the natural logarithm of 2 over root 2, alright? And then you rationalize the denominator, root 2, since you can have a square to the denominator, so you're going to have the natural logarithm of 2 root 2 over 2, and then the 2's divide out, and then your final answer is a natural logarithm of root 2. So your answer is, what is it? It's option A. Alright, so there you have it. Alright, let's take a look at the next question, question 30. It says, alright, so 30 says if a function f is continuous for all x, and if f has a relative maximum at negative 1, 4, and a relative minimum at 3, negative 2, which of the following statements must be true? So we have a max and a min. We have the points where they happen. So how about we draw a sketch of the situation and see how we can use that to solve this problem, alright? So let me draw a coordinate system for you. So we have negative 1, 4. Right here, negative 1, it's not drawn to scale, okay? So negative 1, 4, this is 1 point. We have a max over there, and then on 3, negative 2. 1, 2, 3. We have another point here, -2. Okay, so most people, when they see this problem, instinctively you say, okay, this is a max. It's going to look something like this. You have a max there. It's continuous, right? So it does whatever it does. It could sweep around here, but that's a min, so it goes like that. Okay? So if this is an accurate sketch of the situation, then since it was concave down here and concave up here, and the function is continuous, you would expect there to be a point of inflection somewhere between 1 and 3. So option A will work. F prime of 1 will be 0. This will work also. The graph of f has a horizontal asymptote. Well, absolutely, you have at least one, right? Wait, actually, so I thought it said horizontal tangent. No. So horizontal asymptote, we don't really know. We can't really say that for sure here. Horizontal tangent, yeah. Okay, so this is one possible sketch of the situation that we're dealing with, and we notice that it satisfies three criteria. But another sketch of the situation is something like this. What if we had one of the points, the first point was just an endpoint like that, and then uh, at the other point where it's 3, what if the curve looks something like this? You have a minimum here, and then it just goes straight, bam, and stops there. Okay, that's a maximum, right? And this is a minimum. You notice that it satisfies option D. It doesn't satisfy B. And if it's straight enough, it won't satisfy A either. All right. So you've seen how the different cases we have could be made to satisfy. We can customize this problem to satisfy one condition and not the other. Well, we want to be able to be sure that, or we want to pick a case that is always true. Okay, well, do you notice? Let's take a look at option E though. It says the graph of f intersects both axes. Did that happen here? Absolutely. Did that happen here? Yeah. Okay, using the intermediate value theorem, you're going from one quadrant to another quadrant. You guarantee to have a value of C that's gonna be in between these two. Okay, so it has to intersect on both quadrants in order for you to travel continuously from quadrant 2 all the way to quadrant 3 because this function is continuous. All right, so let me show you a scenario where it actually doesn't meet any of these criteria but only satisfies this. What if we had a situation where the graph looks like this? We have the 2 points. The max is right here. This is 1, 3, and actually -1, 4, and then this is -2 and 3. Now what if we have just a straight segment from here to here? Okay, what if we have a straight segment? Do we have a tangent line? We have something like this. Do we have a horizontal tangent anywhere here? No. Is f prime of 0, is f prime of -1 0? Absolutely not. But we can clearly see that since this function is continuous, it has to intersect both axes. All right? So this clearly shows that option E, so this is wrong also, and that's wrong. Option E, by the intermediate value theorem, clearly shows to us that this function will have to intersect both axes. All right? So there you have it. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. And please post a comment down here to let me know what you think about this presentation. More clips coming from markbusser.com. Thanks again and have a wonderful day.